Hi everyone. So we are continuing our SVM classifier again today. So we have a continuation of SVM classifier. So far you have learned about preliminaries of SVM classifier. So what we have learned is that if we have two attributes in a two-dimensional space, x1 and x2, and if we have two types of data points, for example, some are here and some are there. So we have some blue data points and then we have some red ones. Then we can have a separator line between these two sets of data points or these two classes. And we have learned that we can write this line, the equation for this line as vector w x plus b is equal to 0. So any data point that is on the line follows this equation, and any data point that is not on this line, either on the red side or on the blue side, follows another kind of equation. So if we are on the red side, for example, we have wx plus b is less than 0 for the red part, and for the blue ones, we have wx plus b is more than 0. We also have learned that we can have explain parallel lines to our separator line like this. So for example, we can have two parallel lines, and the red one, for example, all the points on the red line they have this kind of equation, plus b, for example, is equal to -1, and if the blue one has the same distance from the black line, then we have wx plus b is equal to 1. Okay, it can be -2 and 2, -3 and 3, etc. So the point is that the parallel lines to our black line, their equation is different from the original black line in this constant that we see here. Also, we have learned that we can calculate the distance between two parallel lines. So basically, if I have this black line here, and then I have two parallel lines with the same distance from the black line. So in our example, when we have -1 and 1, this distance is actually equal to 1 over norm of w. We have learned that also in last video. And this one is also 1 over norm of w. So whenever we have this kind of situation, we call this area the margin area. So it is a margin around the black line, and one side of it is the red, the other side of it is the blue. So this is the margin that we have. So far, our examples were all in two-dimensional spaces. So in a higher dimensional space, sorry about that, in a higher dimensional space, so suppose that we have a three-dimensional space. We have x1, x2, and x3, and then we have some blue data points in some part of the space and in some red data points in another part of the space. The separating line, instead of being a line, it's going to be a separating hyperplane. So we are going to have a plane that separates these two classes from each other. So we are going to have a hyperplane in the d-dimensional space. So we can again represent this hyperplane with a similar kind of equation. We are having wx plus b is equal to 0, but this time our w is three-dimensional. So we have w1 x1 plus w2 x2 plus w3 x3 plus b is equal to 0. If we have d-dimensional space, we are going to extend this hyperplane into d-dimensional space, and we represent it with d-dimensional w's and one b. So b is just the offset. This is one scalar, and w is a d-dimensional vector. All the points that are on this hyperplane, they have this equation wx plus b is equal to 0. So if we call h of x, for each data point x, we can calculate this function h of x wx plus b for x on the plane. We have h of x is 0. For the x on one side, we have h of x being larger than 0. So for example, here on the red side, in our example, on the red side, we have h of x larger than 0. And for x on the blue side, we have h of x less than 0. Okay, so this is basically what we need to know about more dimensional spaces. Okay, so going back to our two-dimensional case, we said that the goal of SVM is to separate our data into two classes, right? And we have seen that actually any data point that falls on one side of our separating line is going to be assigned to one class. So for example, here on the negative side, it's all red, and any data point that falls on the other side is going to be all blue, and it's going to be all another class. Now, the question is, okay, how do I choose this line? Because suppose that this is my x1, this is my x2, and then I have two red data points here and one blue data point there. I can have so many different lines that separate these two classes from each other, right? So I can have this line saying wx plus b is 1, or is 0. I can have this other line, wx plus b is 0. So this is like w of line purple and b of line purple. This is w of line black and b of line black. Or I can have, for example, this line, w line green x plus b line green is equal to 0. All of these three lines are actually separating the two classes for me. So the difference is that they have different directions and different b's, right? So which one is a better separator of the two classes for me? To answer this question, we are going to look at the margins that are going to be created around each of these two lines. Remember that when we had this black separator line, we had two margins around it. One that goes through the red side, the other one that goes through the blue side. And we wanted to have these two separator lines to have equal distance from each other. So now what I do is that I create a margin that is parallel to the line that I have, but goes through the closest data points in each of the classes. For example, for this black line, the closest data point is this one, this red one. So I can have this as a parallel line for my margin here. And then if I have another parallel line, equal distance, I'm going to have this guy here. For the purple one, This blue is the closest data point to it. So I have this much of margin on this side, and I will have another one which is similar on this side. For the green, my margins are going to be like this. Okay, so this is my margin for green, this is for purple, and this is for black. So we can see that for each of these separator lines, we can actually draw this margin around them that are parallel to the original line, but none of the data points from either of the classes are in that margin. In the sense, we say that we have these two margins that are kind of our safety net. If I have my line here, if I move from this line a little bit to the right and a little bit to the left, I'm going to be fine, and because there are no data points in this area of the margin. Then I can say, okay, whatever that falls on this side, on the right-hand side of the right purple margin, is definitely going to be a blue data point, and whatever that falls on the left-hand side of the left margin of the purple line is definitely going to be a red data point. In other words, this part is going to be a safety part for me, just to make sure that if my separator is not that accurate, and we have, for example, one blue data point somewhere very close, then we are not doing that bad in separating this blue class from the red class. So what do we want in SVM? We want to find out which of these separator lines are the best. How are we going to choose the best separator line? We are going to choose the one that gives us the maximum margin possible. So if I have 3 different separator lines and one of them give me a huge margin, then I can say I am separating these two classes with this line, and also I have a huge margin so that it's a wiggle room for me, right? So I have a larger wiggle room, so I'm going to choose that one. Okay, so this is the intuition behind how SVM works. It really is trying to choose the separator line or the classification line that gives me the maximum margin possible. Then, if I find this, then I choose, for example, this black line here. So I have x1, x2. This is the blue, this is the red, and then I have this black separator that I have chosen. The formulation for this black line is Wx plus b is equal to 0, right? Then I can say, okay, whatever that falls on right and above of it is going to be class blue, and whatever that falls on below and left-hand side of it is going to be class red, right? So what we do is that if our data has two classes, for example, black, blue, and red, so we have a data set. Our data set are pairs of x and y's, right? And our yi's are here. They are either blue or red. What we are going to do is that we say, I'm going to translate this blue label to +1 and translate this red one to -1. So whenever I see a blue label, I will, instead of calling it blue, I will call it +1, label number 1. And whenever I see a red, I'm going to call it -1. Okay? Why are we doing that? Because we said whatever that falls on the blue side has this kind of equation that Wx plus b is going to be larger than 0, right? And on the red side, we have Wx plus b is going to be less than 0, right? So if I have h of x for the blue, it's going to be more than 0. If I have h of x for the red, it's going to be less than 0. Also, we know, we just decided that the yi for the blue is going to be plus 1, and the yi for the red is going to be minus 1. Now, it means that if I multiply hx with yi, for the blue class, I'm going to get some number that is positive, right? Because yi is positive, h of x is, yi is 1, h of x is positive, so it's going to be positive. And if I multiply yi with hx in the red class, or the negative class, this is also going to be positive. Why? Because h of x for the red class is negative, and the label for the red class is negative, so two negative things together is going to give us a positive thing. So just keep this in mind for a while, and we are going to get back to it. Now, let's talk about linearly separable classes. If our two data points are linearly separable, we are going to have these two conditions, that whatever that falls on the right-hand side or above the separable line, separating line, is going to be having h of x positive, and whatever that is below is going to have h of x being negative. So far from examples that we've seen, our data has been linearly separable, meaning that we could find one straight line or one hyperplane to separate this data into two different spaces or two different classes, just using one line or one hyperplane. So if I have a data like this, so suppose that I have this, this, and this, and this. So I have this blue and red classes here. I cannot have any line that can separate these into two pure classes, right? Any line that I draw here, I cannot really separate the two classes from each other. So this data is not linearly separable. But for any linearly separable data, then we can find a hyperplane that separates these two data. And if the formulation for the hyperplane is h of x is equal to 0, then we are going to have this situation that if the label is -1, we are going to have h of x to be less than 0 for all of the class -1. And if the label is +1, we are going to have h of x being more than 0 for class +1. So that is for linearly separable data. And then we are going to have a separating hyperplane there. Okay, so we have learned about linearly separable. We have learned here that our SVM is trying to find the line with the maximum margin to the two classes that we have. Now let's see how we can find the maximum margin. To find the maximum margin, we need to find how we can calculate the margin itself, right? So I have two data points here, and I have one data point there, and I'm having this separate, this line wx plus b is equal to 0, that is separating these two classes. Now, the margin that we want to have is going to go through these data points, for example. So if I have a data point in this space that is not on this line, I can actually calculate the distance from this data point to my line, right? We have learned from before that the distance between a point, so suppose that this is point x0, the distance between x0 and this line is going to be wx0 plus b divided by norm of w, right? So the absolute value that we get from wx0 plus b divided by norm of w. But also, we can rewrite this same distance in another way. So we know that wx0 plus b is actually equal to h of x0, right? If this is h of x. Also, we have learned from here that if we multiply the label for any point with the h of that point, we are always going to get a positive number, no matter if the label is positive or negative, no matter where the data point is falling on. So here when we are, this is as if we multiply yi with h of x, it's as if we are taking the absolute value for h of x, right? So here, in calculating the distance, instead of taking the absolute value for h of x, we can just say that we can multiply the label y, right, for this x0 with h of x0 divided by norm of w. And that is going to be equal to our, sorry, it's x0, equal to the distance that x0 has with our separating line. We can also calculate it another way. So if I have x0 there, the distance that x0 has with this separating line is actually going to be equal to the length of this part. What is this part? If we project x0 onto this line, let's call it x0p, we are going to calculate x0 as a summation between the projection of x0 over this line, or x0p, plus some remainder. This remainder is actually equal to this distance, right? Okay, so what is this remainder? This remainder is a vector itself, right? So what we have is that we have this, which is the vector of x0p. So this is x0p. This is the vector of x0 itself, and this is going to be our remainder vector, right? So basically, it is as if x is being the red vector, x0p is the green vector, and r is the remainder vector. Now, r being a remainder vector is actually, so we have x0p vector. This remainder vector, what is it? It is a value, a scalar value, multiplied by the direction of w. you remember that W, direction W, vector W, was a vector that was perpendicular to our line, right? So this R is in the same direction as W. What does it mean, same direction as W? How can we calculate the normalized direction of W? It's basically W vector divided by its norm, right? This is a vector of size 1 in direction of W, and this is a scalar that is going to tell us how large this R vector is. Okay, so this R vector is the directed distance of x0 to the line, and this is the scalar, the value. So from here, if I have x0 written like this, then I can calculate h of x0 as h of x0 projected plus r multiplied by this vector in the direction of W. So we know H is W transpose its input, x0p plus R W over W plus B. Okay, so if I calculate this, it's going to be W transpose x0p plus B plus W transpose R W over norm of W. We know that x0p is on the line for which we had W transpose x or h of x being equal to 0, right? So this part is actually h of x0p. Because x0p is on the line, it is actually equal to 0. Now for this part, we know that norm of W is equal to W transpose W, right? So this whole thing is actually equal to R W transpose W divided by norm of W, which is square root of W transpose W, right? So basically, it is equal to R square root of W transpose W, square root of W transpose W divided by square root of W transpose W. So these two will be canceling each other. So we are going to have R multiplied by square root of W transpose W, which this is basically norm of W. So this is going to be equal to R norm of W. So eventually, what do we have? We have h of x0 is equal to, the first part is 0, the second part is R norm of W. In other words, we can say that because we were looking for this scalar, what is this scalar, or the distance from x0 to our line, right? So R will be equal to h of x0 divided by norm of W. But this is a directed distance, so it can be actually negative. If x0 is below this line, R would have been a negative value. So if we want the non-negative or the distance, that actual distance, then we can multiply this by the class of x0. All right. Okay, so far we have learned that we can calculate the distance from any point, for example, xi, to the separating line like this is going to be equal to, we'll call it delta I, is yi h of xi divided by norm of w. W is in the formulation of the separating line. H of xi is w transpose xi plus b, and yi is the label for that xi. Okay, now that we have this, let's go back to our SVM. We said that the goal of SVM is to maximize the margin. We have the distance of any point from the hyperplane that is separating. Okay, so I have my data points. I can calculate the distance between all of these data points to this line that is the separating line. Then the margin that I'm going to have is going to be the distance, twice the distance of the closest data point to the separating line. In the margin, we do not want to have any data points from any of the classes because this is our wiggle room that we have. So we want it to be as big as possible, right? So we don't want to have any data points from any of the classes. So the margin from the separating line can go as far as it hits a data point from one of the classes. So the closest data point. In other words, the margin, the width of the margin is going to be equivalent with the distance between the closest data point to our separating hyperplane. So if I am given a hyperplane with a formulation, then I can calculate the distance between all of my data points with this hyperplane and then select the minimum of those distances, and that is going to be my margin because that relates to the closest data point that is going to be to that hyperplane, right? So actually our margin, we're calling it delta star, is the minimum of all yi multiplied by hxi divided by w's that I can get going over all possible xi's that are in my data. So it is basically the minimum of yi w transpose x plus b over w's that I'm going to have over all xi's. So this is my margin. Given any line, I can calculate this margin for my data points. Now in SVM, our goal is to select a line, right? So if I have two different lines, for example, I want to choose one of them as my separating line, as my classifier. So which one do I choose? I'm going to choose the one for which the margin or this delta star is the maximum. Okay, so our goal in SVM is to maximize this delta star. So I want to find the W and B that maximize this delta star. Another thing is that whenever we find these xi's, that the margin is the distance between those data points and the line that we have, for example, this one, these xi's are going to be called our support vectors. Why? Because these are the vectors that are supporting our margins, right? So for example, let's look at an example in slide 59 or slide 60 actually. In slide 60, see, when we have this red separating line, the margins can go away from this line as much as they hit these data points that are the closest or supporting these margins. It's as if these lines are kind of having the margin on top of them or supporting the margin so that it doesn't move beyond them. So that's why these data points are called the support vectors in SVM. All right, so far we have learned that SVM's goal is to find the line that maximizes this margin that we have with the data points that are in our data set in the two classes. All right, so we also have learned that the margin that we are going to have is going to be equal to the minimum distance among all our xi's, which are our data points, and the distance is defined as their label, yi, multiplied by h of xi, divided by norm of vector w. That vector w is explaining this separator for us. And this minimum distance is going to be equal to our margin. And also we have learned about the concept of support vectors. So we have learned that our support vectors are the data points that have the minimum distance with the separating line, and they are actually somehow supporting our margins. Okay, so basically, if I have my minimum distance equal to delta star, so if I have defined that, then the support vector's distance with the separator line is going to be equal to delta star, which is the support vector's label multiplied by W transpose multiplied by the support vectors as x star plus b divided by norm of W, or it's equal to y star h of x star over norm of W. That is the distance between our support vectors to our separating line or classifier in SVM. Now, the goal that we are going to have so far then is that if we want to formalize our SVM goal, so far we had said that we want this delta star to be maximized, right? So we want to maximize delta star, but at the same time, what we want to do is that we want to separate the two classes, right? We cannot select a line that maximizes this delta star, but it does not separate the two classes. So we have to put that into our optimization also. So we say, while we are maximizing this delta star, we also need for all of our data points, their yi multiplied by their h of x, or it's equal to W transpose x plus b, to be larger than or equal to 1. For all xi's that are a part of our data set. Okay, we have learned that for all of our xi's that are not on the support vectors, we have these more than 1, so we have learned about them here. We have learned that all of them are more than 0 or less than 0. If we have the borders, if we have the margin equal to 1, then they are going to be more than 1 or less than 1. But for the ones that are on the margin, we are going to have them equal to 1. So basically, what we are going to have is like this. If I have this separating line, then I'm having these margins. And if this is W transpose X plus B is equal to 0, if I set this one, W transpose X plus B is equal to 1, and this one as W transpose X plus B is equal to -1, then the support vectors that are on the margins are going to have, for these guys, they are going to have W transpose X plus B, YI, XI is equal to 1, right? Because for these, it's W transpose X plus B is 1, and then their label is 1. So 1 multiplied by 1 is 1. For this one, W transpose plus B is -1. The label is -1. -1 by 1 is going to be equal to 1. For everything that falls kind of farther than the margin, no matter what kind of label it has, we are going to have YI, W transpose XI plus B is larger than 1. Why? Because for these guys, if they are on the blue side, H of X is going to be larger than 1. If they are on the red side, H of X is going to be less than -1. Right? So when we multiply them with their label, then they're going to be more than 1. All right. Now, where from did I get this 1? Let's look at where from I got these parallel lines that they have 1 here. Didn't we say that we want to maximize the margin? Then why do we have 1s here? Let's see why we have that. We said that our separating line or our classifier has this format. H of X is equal to W transpose X plus B equals to 0. So I can write this line like this. The thing is that if I multiply H of X, like sides of this equation, with any constant S, I still get this equation to be equal to 0. So if I say S multiplied by H of X is equal to SW transpose X plus SB, it will be equal to S by 0, which is 0 itself, right? So what I can do, it's as if I can have another line that it's W, the direction is SW transpose, and the bias or intercept is SB, and I still have the same separating line, right? It's an equivalent hyperplane to what I was describing. So how can I fix that? The way I can fix that is that I can say that I will choose one out of these hyperplanes in a way that, for example, my distance between the two margins is actually equal to the distance between margin and my line, separating line, is actually equal to 1 over norm of W. In other words, what I will do is that I will choose a canonical or unique hyperplane by fixing S. So I will say, okay, I want to choose S such that the distance of support vectors with the separating hyperplane is 1. Okay, so I just choose 1 here for having an easy calculation. So what I do is that if I choose S in a way that if I have this data point as my support vector, I have the distance between the support vector with separating line as 1. Okay, this is the absolute distance. So if I choose S is equal to 1 over the label of the support vector multiplied by h of support vector, then what I'm going to have is that I will fix this h of x in a way that the margin is going to be equal to, again, we know the margin is actually equal to y star h of x star divided by norm of w. And if I choose S like this, then I'm going to have this as equal to 1 over norm of w. Right? So in this way, what I'm going to have is the two margin lines that I'm going to have are going to have this equation of W transpose X plus B is equal to 1, and this one is going to be W transpose X plus B is equal to minus 1. So overall, what I'm going to have is that I am trying to find a W such that we are going to have maximum of margin that maximize the margin, and at the same time we want for all data points that we have YIHXI to be larger than equal to 1. Okay, so basically our objective is going to be finding W as the argument that maximizes W and B as the arguments that maximize the distance with the margin is now fixed 1 over W. And then we have these conditions that YI W transpose XI plus B are all going to be larger than or equal to 1. So this is the SVM's objective function. This is what we are going to do, how we are going to find this separating line that is SVM. Okay, so when we have a separable case, we are going to see an example like in slide 71. We are trying to maximize the margin here, which is basically 2 over norm of W because we have 1 over each side, but it doesn't matter if it's 1 or 2, the maximization result is the same, subject to WXI plus B, if we multiply them with their label, is going to be larger than or equal to plus 1. Okay. Now, finding the solution for this maximization problem is difficult because we have this W down below. But what we can say is that if we want to maximize 1 over norm of W, it's equivalent to if we minimize the norm of W itself, right? Also, so I'm trying to find the W and B to minimize W. Also, we can have an equivalence if we minimize W squared, right? The W that minimizes norm of W is the same W that minimizes the norm of W squared, right? The reason we do this, we square this, is just to have an easier and convex quadratic optimization. Okay, so this is just to make our optimization easier. We still have the constraints that are linear constraints here, but at least this formulation that we have here is easier than the form that we had above. It's easier to optimize. Okay. All right. So let's try to see how we can find W and B using this new optimization objective function. So now we want to minimize norm of WX squared such that we have these linear constraints. How can we take care of these linear constraints? Is that we use a specific method called Lagrangian. So what we do here with Lagrangian is that we add the constraints to the objective function directly, and we just add some other conditions. So the way we are going to introduce some parameters, alpha i's, for each of these constraints that we have, yi w transpose xi plus b, okay, and then we say that at the minimum point, so if we find this argument that minimizes w squared, this alpha I multiplied by yi w transpose xi plus b should be equal to 0. This is called the KKT condition. And also we use the same alpha i's to add these conditions to the objective function. So our objective function now is going to be equivalent of this w squared that we had from before minus sigma alpha I yi w transpose xi plus b minus 1. All right. Okay. So now we have to minimize the objective function with respect to w and b and maximize it with respect to alpha i's, and that would be our solution for this new objective function. So this is called the Lagrangian, and the alpha i's are called Lagrange multipliers. This is one way to solve the constraint optimization problems. Okay, so now what we have is that we want to find the W and B that minimize W squared minus for all i's in the data 1 to n. For each data point, we have one of those, right? One of these constraints. Alpha I, yi w transpose x plus b minus 1. We want to minimize this. How do we do that? Again, because it is a convex optimization function, what we can do is that we can just take the derivative of this with respect to w and with respect to b and set it to 0 and solve for it. So our L, which was this, is w minus sigma I equals to 1 to n alpha I yi w transpose x plus alpha I yi b minus alpha I, right? If I take the derivative of L with respect to vector w, I'm going to have, this is a vector derivative of w, it's going to, w squared is going to be equivalent to 2w. And in this sigma, the only term that has w is this one. So we are only going to take the derivative of this one with respect to w, which is I equals to 1 to n alpha I yi x, right? This is the derivative with respect to w. Now, if I set this to 0, because I want to find the minimum point, right? So if I set the derivative of WL with respect to W equal to 0, then I have 2W minus I equals to 1 to n yi alpha I x is 0. So I can have W is equal to 1/2 of sigma I equals to 1 to n alpha I yi x. Okay, so this is for my W. Now for B, if I set the derivative of L with respect to B to 0, if I take the derivative of L with respect to B, the only term that has B in it is this one over here. So it's equivalent to minus sigma alpha I yi I equals to 1 to n. So if I set this derivative to 0, then I have sum of I equals to 1 to n alpha I yi is equal to 0, right? This is what I get if I set the derivative of L with respect to B to be equal to 0. Okay, so does this give me the solution right away? Well, no, it doesn't. Why? Because I don't know the value of alpha i's. I know yi for all of my data points. This has I in it. I have xi for all of my data points, right? But I don't have alpha, so I don't know how to calculate w yet. Similar for b, when I take the derivative of L with respect to b, I don't have any b in this solution that I see here, so I cannot really find b. But is the result that I get so far, are them useful or not? Well, yes, they are. Why? Because look at w. What you see here is that w, vector w, is actually a linear combination of all of my data point vectors xi's and their label, right? And the way that they are combined together is using the multiplier alpha i's. So that's one. That's an interesting result. So we can express w as a linear combination of all of their data points with the Lagrange multipliers as the coefficients. And also, we can see that the sum of the Lagrange multipliers with the labels is equal to 0. It means that the Lagrange multipliers are kind of distributed evenly between the positive one class and negative one class, right? Okay. So far we have this result, but also we don't know w. We don't know alphas, right? We need alphas to be able to figure out w, for example. So how can we solve for alphas? Okay, so now we want to find out what alpha i's are. So we had L is equal to this sum of w minus sigma alpha I yi w transpose xi plus b, right? That was minus 1 actually. So we have here, yes, this was our L, and we have to maximize L with respect to alpha I to get the optimum value for alpha I. Now, what is the optimum value for alpha I? Again, we can take the derivative of L with respect to alpha I and set it to 0, right? So if I do that, I will have something that has W in it. Before I do that, actually, what I can do is that we can put the value that we find for W above here into this equation. So let's do that, first of all. So L is actually, let me open this sigma a little bit, is equal to W squared minus sigma alpha I yi W transpose xi minus sigma alpha I yi b plus sigma alpha I is 1 to n, 1 to n, 1 to n, right? Now, because I know that W is actually equal to 1/2 sigma alpha I yi xi, I just calculated it above there, right? This is my W. Then I can see that this part is actually equivalent to sigma W transpose W, right? Because these three are going to give me W, and I'm multiplying with W transpose. So I'm getting this here, and of course 1/2 of it. And then what I'm going to see here is that I have learned from above there that sigma alpha I by I is actually equal to 0. So I know that this is equal to B multiplied by sigma alpha I by I, because B doesn't have an index for I, right? I can put it out. So this is 0. So this whole thing is going to be 0. So what I'm going to have as L is going to be equal to W, norm of W, minus 1/2 sigma W transpose W, I 1 to N, plus sigma alpha I 1 to N. Right, so we got from this L, by putting back the results that we got from the previous section, we got from this L to this new L. Now, again, if I put back this into this equation, because I want to represent the L that I have only based on alpha, so that if I take the derivative with respect to alpha, I get whatever that is in terms of alpha without depending on W, so that I can calculate alpha i's directly, right? So what I will get here is going to be L would be sigma alpha i's I equals to 1 to N minus 1/2 sigma I 1 to N, J 1 to N, alpha I alpha J, yi yj, xi xj. Okay. Now I have an objective function that is explained only in terms of alpha i's and alpha j's, and then I can actually solve it to find the best alpha. This formulation is called the dual formulation here. Why? Because it's the dual of the original L that we had. The original L was not only in terms of alpha, but we have this formulation now of L that is only in terms of our Lagrangian multipliers. It also has some constraints. For example, the constraint is that alpha I y i's should be, summing of them should be equal to 0, like what we had above. And by the way, the Lagrangian constraints are always larger than or equal to 0. Okay, so we can solve this formulation and easily get to the value for all of the alpha i's. And then after we found alpha i's, we can put them back into this formulation for W. Now I have xi's, it's my data points, yi's is the labels for my training data points, and I have calculated the alpha i's, and then I can find W according to that. So I can have this separating hyperplane. But what is the issue here is that look at the number of parameters that I have to learn. I have to learn n different alpha i's because we have an alpha I for all data points, right? Because we define this alpha I as a constraint for all of our data points. We want to separate all of our data points, so we want to make sure that for all of our data points, we have this constraint. For each of them, we created a Lagrangian multiplier. So we need to learn at least n parameters here, or order of n parameters, to be able to find W and B. It means that we have to go over all of our data points. It's a little bit daunting, right? How can we solve that? Let's go back to where we introduced the Lagrangian multipliers here. You remember that we had this KKT condition when we were introducing that. And this was, oh, actually it has a -1 here. This was basically saying that alpha I multiplied by yiw transpose xi plus b minus 1 should be equal to 0 at the minimum point for L. So if we find the best W and B, we are going to have this equation that for all of the data points, this is equal to 0. Now let's take a closer look to that. So the KKT condition is saying that alpha I yi W transpose xi plus b minus 1 is equal to 0. Okay, so if I have this equal to 0, alpha I is a scalar, right? yiw transpose xi plus b minus 1 is also a scalar. If I have two scalars multiplied by each other equal to 0, it means two things. Either alpha I is equal to 0, or yiw transpose xi plus b minus 1 is equal to 0. Okay. So let's look at this one, the lower one. If I have yiw transpose xi plus b minus 1 is equal to 0, it is equivalent to having yiw transpose xi plus b is equal to 1. I have seen this somewhere else. Where did I see that? I saw this as the equation for the margins that I had, right? So if we are on the positive margin, we have W transpose xi plus b is equal to 1 and yi is equal to 1. So basically, we are going to have yi dot W transpose xi plus b is 1. If we are on the negative side, we have yi is equal to minus 1. W transpose xi plus b is minus 1. Again, we have the same thing. So whenever we see this, it means that we are talking about data points on the margin. We had a name for that. What was the name? They were support vectors. So for our support vectors, we are going to have this part of equation to be equal to 0. But then for the non-support vectors, when we don't have this, we should have alpha i's equal to 0. Right? Because the only points for them that this is happening is for the support vectors. So for the rest of the data points, we should have alpha i's equal to 0. What does it mean? This is an interesting result. It means that if I have two sets of data, the red ones, two classes of data in my data set, and the blue ones, and I have this SVM classifier with these two margins. Suppose that this is here also. For these support vectors that I have here, I already have W transpose xi plus b minus 1, yi is 0. And for all the rest of the data points, for these ones and for these ones that are farther from the margins, I have alpha I is equal to 0. Okay, that is interesting. But what else does it mean? Remember that when we had W, when we were calculating W, we said W is equal to sigma alpha I yi h, xi, or half of it. It's the 1 to n, right? We had that. Now, knowing that the alpha I for every other point other than support vectors is 0, it means that instead of going for the summation from 1 to n, the only thing that we need to know is for the support vectors, what is the alpha I, yi, and xi? That's one thing. And also, we don't need to find alpha i's for all of our data points anymore. We just need to calculate alpha i's for our support vectors. That is way easier, way less number of parameters that we need to learn, because we know alpha i's for the rest of the data points is they are all actual to 0. Okay, so this is a very interesting result that is going to help us solve our problem way easier. Now we have found W. How can we find B? Right? To find B, we just use each of the support vectors to find the B for them. Now I know what are the support vectors, so I will say I know that yi W transpose xi plus B is equal to 1. I know W, I know xi, I know yi, so B for the support vector I is equal to 1 over yi minus W transpose xi. Yi is either 1 or -1, right? So basically it implies that it's equal to yi, because 1 over 1 is 1, 1 over -1 is -1. So it's yi minus W transpose xi. So for each of my support vectors xi, I can find a bi. These are going to be close to each other anyways, but I'm going to take the average of those over all the support vectors for which alpha i's are positive, and I will set my final B to this. Okay. Okay, so that's nice. Now I have my W, I have my B, so I have the separating line. I know for any data point X, I can calculate W transpose X plus B. The ones that are on the separating line, this is going to be equal to 0. For the ones that are on the margins or support vectors, this is going to be equal to 1 or -1. Now that I have found this, how can I use it to actually classify some new data points or some test data? The way that I can do that is that for a new data point, suppose that it is called Z, I can actually calculate h of Z. And then I can say y, the predicted class label for this data point Z is sign of h of Z for me, which is sign of W transpose Z plus B. It means that if W transpose Z plus B returns a number that is positive, then the class label is going to be +1. If it returns a number that is negative, the class label is going to be -1, right? That is easy. So for example, if you check the slide, this slide on the left, you can see that we have this W transpose X plus B equal to 0 and its margins that are +1 and -1. Now consider this Z over here. If we calculate the h of X for this Z, it is going to be larger than 1. So the class label that we assign larger than 0, sorry. So the class label that we assign to this Z is going to be equal to +1. But if Z is on this side, then W transpose Z plus B is going to be negative, so the class label is going to be -1. What happens if Z is here? So the W transpose X plus B for this Z is going to be still negative, right? Because it is on the right lower side of our separating line. It's just going to be less than -1, right? It is within the margin. Although it is within the margin, we can still classify it correctly and say that this is belonging to a negative class. So this is how our SVM works, but there are some challenges with the linear SVM that we have. The first challenge is the non-separable case. So for whatever we have seen so far with the objective function and everything, we made sure that our classes are separable, meaning that if I have a line, I have one class on one side of the line and the other class on the other side of the line, right? But what if I have a non-separable case that we have seen an example of before? Or in this picture, you can see one of these red class members is on the blue side. What should I do? Should I draw this kind of a very twisted line to take care of it? Well, that could be an option. Another option is that we can stick to a straight line still, so we can have a linear SVM, but we can allow a little bit of a training error. So we can say, okay, I'm fine if one of the data points is misclassified, but I want to keep my classifier simple. But if I had the original formulation in this case for the linear classifier, I could never find a solution. The second challenge is that suppose that the two classes are separable, but the margin is really small. You can see in this picture here on the left that we have the two classes separable, and this black line is actually separating them. But the data points, the support vectors here are too close to each other. We don't have much of a wiggle room. So again, it may be too tight for us. While if I had allowed for a little bit of error, and I had, for example, this linear classifier, I would have misclassified this one data point. But on the other hand, I had at least a larger margin if I ignored that one data point. Okay, so basically we have to live with the imperfection. We have to allow for a little bit of an error or cut some points, some slack, so that we can have a larger margin or we can have a bigger wiggle room. Later, we are going to learn why we prefer a big margin and a small training error.